here is Kevin O'Brien from CUNY. He will visualize the sum product conjecture. Please.
Thank you for that stirring introduction. Let me see, Zoom is always nasty with the windows. Okay, so ready to go. Almost ready. All right, so this is gonna be a survey of the sum product conjecture. There's gonna be some math here that's not widely known and pictures that I haven't seen anywhere else, and hopefully they'll provide some intuition. And this is an XKCD comic that's on topic, I guess. Part of the notion when I was looking at the sum product conjecture was that we don't really have good examples for what's going on. And we all have this thing in our head, an idea of what a random set is. But when you try and get specific about what a random set is, it's not a thing, it's a process by which something gets generated. Okay, so the curtain business, that's just hiding some code that makes the whole thing work later on. That has nothing to do with anything. Okay, so here is the conjecture. It's as Mel was saying in the smooze session, it's Paul Erdős alone. And in his phrasing, so it's let A1 through AN be a sequence of n numbers. Consider the numbers AI plus AJ, AI times AJ. And I conjectured, he wrote, there aren't very many people who can get away with using I in a math paper, but Erdős is one. I conjectured about 18 months ago that there are more than n to the 2 minus epsilon distinct numbers amongst them. Okay, and yeah, so we rephrase this usually in current work in the way that I have at the bottom. For every epsilon greater than 0, there's a k naught, such that if A is bigger than k naught, then one of the sum set of the product set is at least k to the 2 minus epsilon. So there's a couple of things worth noting here. Erdős seems to be talking about the union of the sum set and the product set, but when we're talking about the size of the union, so crudely, it's just dominated by whichever one is biggest. And the justification that is almost always given for this conjecture, the only justification I've ever seen given for it, is that if you try and make the sum set be really small, then it's basically an arithmetic progression. And this is the multiplication table problem, another Erdős problem, that pushes the product set up to around k squared over there's some logarithm factors in there. And on the other hand, if you try and make A times A small, well, when it's as small as possible, it's a geometric progression. And if it's a geometric progression, then the sums should be going crazy. And they actually do. That's a theorem of Chang, I believe, is the earliest explicit version of that. So there's these two extremes, right? Arithmetic progressions, which make A plus A linear, and geometric progressions, which makes A times A linear. And in both of those cases, it's been worked out, and it holds. And people kind of leap from there to this conjecture. But to my mind, that dichotomy between arithmetic progression and geometric progression is justifying 1 plus epsilon. It's not justifying 2 minus epsilon. Right? Once you get off of linear growth in one of these, then that logic really doesn't apply very tightly anymore. But we do have a thing I want to focus on here is that we're looking at these pairs. You fix a set A and you look at the pair, the size of the sum set and the size of the product set. So here's some definitions just to help us help me express what I'm talking about. So the sum product pairs for K are all the pairs that you can get as a size of a sum set, size of a product set, where you're looking at sets of positive integers that have exactly K elements. Okay, now as Erdős conjectured, as he stated in his conjecture, it shouldn't matter too much if we're talking about positive integers or reals or complexes. 99% of what I talk today is going to be about positive integers.
Then,
Yes,
if you want,
somebody has
Kevin?
chatted, are we supposed to be looking at slides? As far as I know, you have a slide in front of you right now.
Yes, most of us do at any rate. Can I ask something?
Absolutely.
If you want particular configurations for the sum and the product, I mean, if you nail it down very particularly, you need to use algebraic numbers. If you have, very specific values for the sum and the product, sometimes there's only one configuration that works. And it's you get algebraic numbers necessarily.
Okay, yeah.
So I mean, it's not that it doesn't stay at the same level of generality if you insist that everything be integers. Maybe the inequalities, but particular equalities often do require more general things than integers.
Oh, yes. Yeah. So I'll come back to that, right? That this SPP, the sum product pairs for positive integers, is not the same as even for non-negative integers, and is different again if we're looking at positive reals.
I mean, the reals don't give you anything more general than algebraic numbers. Anything that can be done with real numbers can be done with algebraic numbers. Think about it. It's equations. Yeah. So you can always solve them with, algebraic.
I concur. Okay, but it's worth noting, I guess, in this discussion that often in the work in these problems, you're taking logarithms of things to transform a product set into a sum set, and those logarithms might not be algebraic numbers. In fact, typically they won't be if you started with algebraic numbers. So there is some value to scaling up in generality now and then. But for right now, let's just focus on positive integers. So there's some trivial bounds for the sum set. It's at least 2k minus 1. Throughout this talk, k is going to be the size of the set. And if every possible pair is distinct, then it's k plus 1 choose 2, the size of the sum set. And it's the same thing for the product set. It's just a commutative operation. So we get these, I'll call them the trivial inequalities. Well, there's not quite trivial, but very basic, that lock down this SPP of k, which is talking about positive integers, to being in this square in the plane. All right, so let's take a first look at some of these. Oh, before I come to that, I just want to mention that we have, there are some symmetries here that are worth noting, right? So if we dilate a set, if we multiply everything by the golden ratio or 17, that doesn't change the size of the sum set or the size of the product set. If we translate a set, that leaves the sum set being the same size, but it changes the product set. And then there's also a more subtle transformation. If you just think about, if you take the prime factorizations of each number in the set and you shuffle the primes somehow, but keep the factorizations the same, then the product set is going to stay the same size, but the sum set goes haywire. Okay, so there's some symmetry coming up even amongst the symmetries of the symmetries. Okay, so let's take a first look at this for small k, tiny k even. So SPP3 up here, can you see my mouse pointer?
Yes.
Yeah, okay, so SPP of 3, these are 3 element sets, and we're looking at the pair of the size of the sum set, size of the product set. That's essentially trivial to work out. SPP4 is not quite trivial to work out, but I will do it in full in just a second. There's in the chat, okay. SPP5, I've written some code that I think proves that this is the correct thing, but the code isn't going to convince anybody because it's all spaghetti and held together with baling wire. These others on the bottom row for k equals 6, 7, and 8 are, so I should talk about where these are coming from. I have at this point looked at approximately 10 trillion sets of integers. And for each of them, I've computed the size of the sum set, the size of the product set, and I've put it into the database if its maximum element is smaller than what was already in the database, or if there was nothing in the database. So these 6, 7, and 8 are truly just my imagination of how I can generate random sets that are of interest for this problem. And there's no real reason to believe that, well, as I say, there are more things in heaven and earth that are dreamt of in your philosophy, and there are more sets in the integers than I can imagine. Just kind
I'm
of,
sorry, Kevin, I missed something. So when I look at SPP6, what
Yes.
are the numbers on the axes meaning?
so the horizontal axis is the size of the sum set,
Okay,
and the vertical axis is the size of the product set.
so these are the numbers that come up,
Be a certain
not frequencies, but these are the numbers that come up for different 6-element sets of positive integers.
Yes. And I don't even know how to, you talked about the frequency with which they come up, and that frequency would have to take place in the context of a particular way of generating these sets. And I don't know any reasonable way to generate them.
So it's not like you put in your program, try all 6-element sets where the numbers are between 1 and 100. And then
I've
for
done
each
that.
set-
But and I'll come to that in a bit, all the different things that I've tried. And hopefully somebody will suggest some more things to try.
I do have to ask you one thing. In your slide for 8, there's a sort of isolated dot. See what I'm talking
Yes.
about? Do you believe
Yes.
it? Do you think it's isolated?
No. So 6.
It's just luck that you didn't find the ones in between, right? I'm guessing.
Yeah, I'm guessing also.
Uh-huh.
It would certainly be surprising if it's so delicately positioned right there. But if we're talking about 8-element sets, there are infinitely many of them. And the question is, how do you generate ones that are of interest? Okay, so one thing that's coming up in these pictures is that each of these, for each K, it looks like a flag, right? We've got a flagpole down the right side, and then the flag is off to the left, and maybe it's a little tattered on the end. So, like that kind of a picture, right? Flagpole with the flag flapping. All right, so so let's see, what did I want to mark here? I'm going to prove SPP3 of for K equal 3 and K equal 4. This database that I've got, I've generated 10 trillion sets, so that includes, I'll get into more specifics later, it includes all subsets of the numbers from 1 to 36 have been looked at. Sets of divisors have been looked at. Sets of smooth numbers have been looked at. And random subsets of, k-element sets of the numbers from 1 to n for many, many n's and k's. So I've tried hard to generate these things, but always in having a method of generating them, not just completely ad hoc throwing things in. Okay, so the first thing is to prove that this flagpole structure is real. That's not just my lack of imagination. Okay, so one thing I can't do in Mathematica is the slow reveal, where you only see the top of the slide, and then I press a button and you see a little bit more of it. So you get the whole slide all at once. So here's a result. This was discovered about a year ago by, as far as I know, this is Alex Rice leading a bunch of undergraduates in an REU. I have some work from this for small Ks that includes this gem. So if A is a set of k positive integers and the product set is less than 3k minus 3, then A is a Sidon set. And part of what makes this interesting, and this is what I'm connected to what Moishe was pulling up earlier, is that we can't change integers to reals here. And in particular, you can have, well, I give here an example of 5 positive real numbers, R being the solution to R cubed equals R plus 1. The product set is well under 3k minus 3. But we have this sort of nice rearrangement, like 1 plus R to the 4th. R to the 4th is R times R cubed, and you replace the R cubed with R plus 1. You do a little bit of algebra, you get an R plus 1 in a different place that you can turn into an R cubed, and you get that there's some repetition in the sum set, so it's not a Sidon set. And yep, there we go. Okay. Beautiful, beautiful. Okay, and the proof of this, at least if you give me, so I feel like I've heard of this always as Freiman's 3k minus 3 theorem. In the Rice paper, they call it Freiman's 3k minus 4 theorem. I'll go with what's in my head because it's my head and my talk.
Well,
So
it's less than or equal to 3k minus 4. So
yeah, it's whether you like a strict inequality or a less than or equal to. And in English, less than is easier to say than less than or equal to. So I kind of default to less thans more often. So if A is a set of k integers and the sum set is less than 3k minus 3 in size, then A is a subset of an arithmetic progression of length, and we can even say what the length is. In his original paper, and he uses this premise that this is in the integers a lot, and Mel has a proof of this in one of his books, and that also uses the integrality quite a bit. The Math Scinet, the math review for it, describes the proof of this theorem as by exhaustion in both senses of the word, which is an enjoyable turn of phrase. Okay, so there are various proofs of this. This isn't original to me. Here's the one that I came up with when pushed to need this. Is basically you prove a few cases on your own, just by brute force, ball up your fists and get into it. And then you work by induction, right? So you get a set of k plus 1 numbers. You can look at the first k or the last k, and you hope to be able to imply an induction hypothesis to one or both of those. You have a little bit of work to do to show that, when you cut off one of the elements, you still have a small enough sum set that you can use this. But it comes through fairly reasonably. The engine is still using Freiman's theorem, 3k minus 3 theorem in the integers. So Mel, what do you call this? 3k minus 3 or 3k minus 4?
3k minus 4. Less than or equal to 3k minus 4.
There we go.
But I probably use 3k minus 4 because that's probably what Freiman used. So,
yeah. So his original paper is in Russian, and I know there's a translation somewhere in English. So I haven't looked at those closely enough because my Russian is kind of weak to see if he gave it a name. Okay, so I'm not going to dwell on that. We've got pictures to look at. So how does this give us this flagpole structure? If the product set is small enough, smaller than 3k minus 3, well, then we can take logarithms of the elements of A, and that turns the product set into a sum set. Now, this is requiring A to be a set of positive integers, right? So if we're talking about non-negative integers or just integers, then this doesn't fly. But for positive integers, we can take logarithms. That turns the product set into a sum set. We apply Freiman's theorem, which gives the logarithms in an arithmetic progression. Then we exponentiate, and we get our original set in a geometric progression. Without loss of generality, you can take beta to be greater than 1. So you're going from the small end to the big end. And if this is not a Sidon set, then we would have some solution like this, right? So some pair add to the same thing as some other pair, but that is just saying that beta is the root of a particular polynomial whose coefficients are plus and minus 1. And by the rational root test, since beta is greater than 1, that eliminates it. So beta has to be irrational. And here's where we need a little bit of quantifying. Because n is not too much larger than k, the beta actually has, and this set is a set of integers, the beta has to be rational, right? So you can have a geometric progression with irrational ratio that contains lots of integers. You know, like if the ratio is √2, to be trivial with things. Okay, so there we go. That's the flagpole theorem. It says that if the product set, and remember the product set is on the vertical. So if the, can I draw on this? No, I can't. So if the product set is below a certain line, then it has to be the set has to be a Sidon set, which means the dot that it produces will be on the right edge. And for SPP of 3, that eliminates 5, 5, and then I just have to give examples for the others. For SPP of 4, that eliminates all of these things that don't show up as dots, and then we just need examples for the 10 dots that do appear. All right, so that is okay, so that is a complete proof for SPP3 and SPP4, even though they are it's superficially not a finite problem, but nailed down. Okay, so let's think for a minute about SPP5. So there's 27 dots that I've found, and I believe that's all. And to show that each of the 27 dots is in there, I just have to give you a set that witnesses that. And we can think for a minute about what's involved in proving that, for instance, there is not a dot at 9, 13. So 9, 13, that would be a sum set of size 9 and a product set of size 13. So a sum set of size 9 means that the set has to be an arithmetic progression, and that's down to 2 degrees of freedom. And the product set having size 13, that means that we have some product equaling another product, and we have another product equaling another product. We have 2 of those. And in the 2 free variables from the arithmetic progression knowledge, that gives us a couple of quadratic equations in those 2 unknowns. And, well, quadratic Diophantine equations are eminently solvable. The difficulty is that, okay, so what I'm looking at here, this is an addition table for the set A1, A2, A3, A4, A5. And then next to it is a multiplication table. Of course, the top halves are the same as the bottom halves, and we're only counting them, so we can just focus on the top half. So when I say that the sum set is cut down in size, that means that some entry here is equal to some other entry, like maybe 2A3 equals A1 plus A4. So that's a linear equation. So we start out with this 5-dimensional space for A1 through A5, and each equation cuts that down by a dimension, unless it happens to be redundant, and then it doesn't cut it down. Right? So you just have to go through enumerating all the possible ways that these could be equal to get the sum set down to the right amount. For each of those, you do this easy linear algebra problem, finding a null space, essentially. And that gives you just a few parameters so that when you look at the multiplication table, you just end up with quadratic equations in 2 variables or 3 variables or maybe 4 variables. And each of those can be solved. Okay. Easily enough over the integers or over the reals. So I have, I think, code that has convinced me that my SPP of 5 is correct, but a proof is a social thing, and I don't think my code would convince anyone else because it is all over the map and spaghetti and thrown together over different ideas at different times. Okay, so
what you're
before I
saying
leave
is on
tiny
your
K behind,
SPP5 picture, if you didn't have a dot there, it's impossible for there to be a dot no matter what step you pick.
yes. So I've proven that to myself, but not in a way that would prove it to you.
Do you have an understanding of the tatter? That is to say, the line, vertical line for 13 has a sort of hole in it, 2 places where there are 2 dots that are sort of missing, if you see what I mean.
You mean for 11 here?
No, the height is 13. And
Oh, the height is 13, yeah.
so there's a sort of hole over there, okay? 2
Yeah.
places where you have, for 10 and 11, you have values for 12. For the horizontal axis has 10 and 11. You have on the vertical axis for 12, but not for 13. And you have again for 14. So you have a sort of hole there. You're talking about your tattered flag. That's a hole.
Yes.
Okay.
Yes.
Do you understand why that hole is there?
No.
The particular configurations, why are those configurations impossible? I mean, some configurations correspond to that hole. So that, particular equations that have solutions.
So to show that there is not a spot at 1113, for instance, right? So there isn't just a configuration for the addition table that gives a sum set of size 11, right? There are
Several, many.
I think like on the order of dozens. And then there aren't just, to get the multiplication table to have size 13, there are different structures there, right? So to say that it doesn't exist through the structure of the tables, you're actually saying something about, 1,000 different possible configurations, and each of them is ruled out on its own merits.
Well, sort of. I mean, there may be symmetries there which would allow you to reduce it to, fewer than 1,000 cases, but you haven't actually tried listing those and seeing if there are any symmetries there.
For 5, no.
A real pain in the neck. Yeah. Okay.
Yeah.
And this is just for integer sets.
Positive integer sets with 5 elements. That's what we're looking at on screen. So, it's not like things go crazy, but if you, if you think about this, right? So we've got, 15 elements of interest in the addition table. And each equation comes from a possible pair of them being equal to each other. So if we need 2 of these equations to cut the sum set down by 2, then that's 15 choose 2 squared configurations, and then you've got to multiply that by what's going on in the product set. So yeah, most of those 15 choose 2 squared configurations are you can eliminate by just assuming that A1 is less than A2 is less than A3 is less than A, putting an order into them eliminates a lot of that. But it's still a lot of different types of multiplication tables and addition tables, which have prevented me from being able to answer Moshe's question of why is the tatter happening. Okay, so before I leave back, the absolutely tiny K behind, let me just, these are some questions that I haven't been able to really address here. SPP of 5, again, I think I'll, by the end of the semester, I'll have that code fixed up and it'll be out the door. SPP of 6, maybe my code will be so fast that that will work, but I'm not sure. It's my back of the envelope calculations kind of suggest maybe it will, but probably won't. And 10 is like, I think even if I were a sharp programmer, I would need some really new idea before I could get out to talking about 10 element sets.
Did you ask ChatGPT?
That's where I got the picture of the flag, actually. ChatGPT drew that for me. I had to ask it for a tattered American flag. No, more tatters. No, I need to see the flagpole. And it finally got it up. Okay,
is it possible? Is it possible to keep track of how the complexity increases as you increase the number?
Yeah, well, and so there are a couple of ways to understand that question, right? So one of them is here, this last question. If you're computing one of these SPP of K sets, you know, to see all of the examples, how far out do you need to go? Sets from
You
one
mean,
to.
of course, you mean, of course, the examples that are doable in integers.
Yes.
There are
Yeah,
examples that
positive
aren't.
integers. Yeah. So 1, 2, 3, 4. So to get SPP of 4, I had to look at sets. The biggest element involved is 16. For 5, it's 32. And then for 6, 7, and 8, again, my results are speculative, but it's at least 128, 256, and 1024. So that's one notion of the complexity of these SPP sets, I guess. Another notion of the complexity is just how fast are these things growing. In my database, it's looking like this, so growing kind of, well, not rapidly, right? It does less than doubling at each step. But these are lower bounds, so I don't know what the truth is, and I'd be really shocked if this number 914 actually ends up being the true value. Just because it wasn't all that long ago that this was 152. And I'd already looked at trillions of sets and it was still 152, and then I found another one. So the trivial bound, just because we know that the sum set and the product set have trivial upper and lower bounds, you subtract those and square it, you get this. All the known improvements, including this Sidon exclusion zone, if the product set is too small, then the set has to be a Sidon set. All of the improvements that I'm aware of are little o of k to the 4th. Looking at the size of this, that's kind of disappointingly weak. Okay, so let's get into bigger k. Okay, so as I want k to get bigger, I want to be able to look at different k's at the same time. The sum product conjecture says that I should be looking at the exponent, right? A plus A is k to some exponent, and A times A is k to some exponent, and the sum product conjecture is saying that one of these exponents should be close to 2, at least as the set gets large. So you can get a hold of the exponent by taking the base k logarithm. But if you take the base k logarithm of 2k minus 1, it's not quite 1. It's 1 plus log 2 over log k. And that log 2 over log k is going to 0, but it's involving k in a way that I don't want to. So I've chosen to do this normalization. It's the base k logarithm. But then I apply a linear shift just to get rid of these log 2 over log k's at either end, to stretch things appropriately in between. Won't surprise anybody that M and B are unique. And with this normalization, the absolute smallest the exponent is 1, and the absolute largest the exponent is 2. This normalized version is giving us the exponent and peeling away all the other factors in a nice, smooth way. And I want to define for the pictures these normalized sum product pairs, where I'm looking at a set of sizes, not just one particular size, but a collection of sizes. And that's it. I'm just normalizing the sum set and the product set. So let's look at an example. So this is the normalized sum product pairs for the sets 3 through 8. And this is the Sidon exclusion zone for 8. So in this normalization, the Sidon exclusion zone will shrink. Well, that should actually be doing something. One second, let me see if it does something now. There we go. Okay. So if I, all right, so this are the normalized sum product pairs for 3 through 8, and the sum product conjecture says that as k gets large, all of these dots should be on the 2 side for the sum set or the 2 side for the product set. All right, so let me continue to orient you here a little bit. All the dots along this eastern edge, those all correspond to Sidon sets. The sum set is as large as possible. We have here shown a Sidon exclusion zone, right? This earlier result that prohibits any dots from showing up in there. That depends on k. As k gets bigger, it'll shrink. Along the bottom edge, we have geometric progressions. A geometric progression of integers is necessarily a Sidon set, so we only get that dot in the corner there at 2, 1. Arithmetic progressions are along the western edge, and multiplicative Sidon sets are along the north edge. So maybe we're getting distracted here because we're talking about 3-element sets, right? But if I take them out, that doesn't change much. As I'm taking out the small sets, the things that are left should be at the north and east edges by the sum product conjecture. But it really doesn't look that way, right? It's just thinning out as I go up to only looking at 8-element sets. All right, so that's still kind of tiny, but just orienting ourselves in what's going on. So let's look at a bigger picture. So I have here, this is k equals 7, only looking at the subsets of the numbers from 1 to 36. So here are 8-element sets and 9-element sets. And remember, the sum product conjecture says as the size of the set gets bigger, then these dots should be going to the eastern edge or the northern edge. And 9, 10, 11, well, they're not going east. They're staying up near the top, at least some of them. Oh, and then here I'm talking about 21, 22, 23 element sets, and they're coming south. Okay, so we're not seeing the sum product conjecture take hold here and push things to the sides because looking at subsets of the numbers from 1 to 36 isn't a fair test of what's going on, right? By the time I'm looking at a 27-element set contained in the numbers from 1 to 36, it's basically an arithmetic progression. So the sum set is definitely bounded between 2 and 72, so it can't be very large. And the product set is, well, whatever the product set is, we've got small numbers. 28, 29, 30, 31, 32, and the single 36-element set. Okay, but here's everything all together. All subsets, it's about 69 billion subsets of the numbers from 1 to 36. Of course, it's not 69 billion dots. There's a lot of repetition. Okay, so there are some things here that we see. We see the strict horizontal lines that show up. And we see sort of curving arcs in the opposite direction. And maybe we notice something a little weird going up here in the northwestern corner of the picture. So let's go to the next slide. So here in this slide, right? So I don't want to get distracted by things that aren't really telling me about number theory, right? So this is just a plot of all the possible things from the trivial bounds normalized, right? So this is these grid normalized into this 1 to 2, 1 to 2 box. And we see those same things. We see the lines, we can tell here, maybe they're not quite lines, they're arcing a little bit to the, going from southwest to northeast, and then these stronger arcs coming the other way. So those are all just things about the normalization, right? That those arcs are appearing. We also get kind of a void going along here around 1.16. Again, that's just because this normalization, it involves some logarithms and stuff, and so you end up with some gaps. And this is just for k going from 9 to 12, but the same effect comes in. There's also, I don't know how it looks for you, there's also a possibility that you might start seeing moire patterns, because my computer is showing at a particular resolution, and then Zoom is probably resizing that to a different resolution, and that might give some additional visual artifacts that are just, I don't get to see. Okay, so here's a little bit of a history of the problem before I show some more big pictures. So the question we saw at the beginning is from 1974. Erdős and Simony, the first result, they proved that 1, 1 is not a limit point of these normalized pairs, right? They weren't talking about these normalized pairs, but in this language, that's what they showed. And then Mel, as he was saying, he made that explicit and gave a number 1/32, not 1/2. And showed that it's a void. There's actually no points down there in that corner. And Ford improved that to 1/15. And I have them kind of a little chronologically out of order. Alekesh used a very different technique, I'll talk about that in just a second, to get a much bigger void. And Shoimoshi has done some things to show that very large triangles don't contain any limit points. And well, there have been further improvements past Shoimoshi's that I'm not going to show in the pictures because they're only like moving Shoimoshi's line a non-visual amount, like 1/1000 up. Okay, so some of these results, like there's a collection of them that go through incidence geometry that starts with Alekesh. So you take your points to be A plus A. The first coordinate is from the sum set, the second coordinate is from the difference set. You set up your line correctly, and then you get lots of points from the set P on these lines. And then the Simony-Trotter theorem says that you can't have too many of those. And you chase out what that means, and you get a bound like this, that the sum of the sum set and the product set is at least k to the 5/4. And so that's a void around 5/4 asymptotically, right? So there's no limit points inside that square. This is a theorem of Shoimoshi, where he took this incidence geometry and worked hard at it, and with some cleverness, he broke it into cases, and then each case he could do better. And he ends up with this triangle from 1, 1 to 1, 2, and then 11/8 and 1. Maybe my next picture. Okay, so yeah, I'll come to that in just a second. Okay, so I'll show you these voids graphically in just a second. The best results lately, and there have been a few talks in the seminar this semester about energy, which is a sum of quadruples where the product's equal, and you have a trivial bound connecting energy and the product set. Well, trivial, it's Cauchy-Schwarz. And Shoimoshi gave a clever argument connecting the energy to the sum set, and you combine them all and you get something like this. So Shoimoshi's inequality, if you have a 46 element set, it's still trivial, right? The sum set is at least 2k minus 1. The product set's at least 2k minus 1. And for a 46 element set, that gives us a number that has to be at least 753,000. But Shoi-Moshi's inequality only gives 746,000. So it's worse than trivial for 46 element sets, which is just to say that this void isn't going to show up in these pictures of sets where I'm only talking about 32 element sets, for example. But asymptotically, it should matter. And he gave a nice thing. This is his 4/3 inequality. If you're more into the literature than I've been talking about. Okay, so the data set that I'm about to show you pictures from, I've looked at every subset of the numbers from 1 to 36. I've looked at every subset of the set of divisors of n for n up to 2048, except for a couple of numbers where there are too many divisors for me to look at every subset. And so I've just looked at a random collection of subsets. I've looked at hundreds, maybe thousands of pseudo-random subsets of n with k elements for each k up to 32 and n up to 2048. So that's, doing it for 1,000 and doing it again for 1,001, doing it again for 1,002, and so on. I've got a notebook set up where each time I open it, it just starts running some more. So I've lost track of, and sometimes I change the parameters a little bit. So I've lost track of exactly what I'm talking about here of hundreds of pseudo-random sets. For some arguments, it's thousands, maybe tens of thousands. For every n up to 65,000, I've looked at hundreds of random subsets of the set of divisors. And those are
What
interesting,
size K?
Place from everything else. Yeah, Moshe.
What size K?
K up to 32.
So that's, none of these are K more than 32. Okay.
Yeah, that's, I sort of arbitrarily set that when I started collecting the databases. I figured I would be able to see the sum product conjecture start to grip hold for, maybe 20 element sets, and I would get it really going into the 30s. But now I'm of an opinion that it should be bigger, but
Okay,
but
and you think now K equals 32 is too small to indicate what's happening?
Well, it's too small to indicate what's happening in Shoi-Moshi's argument.
But more generally, for the sum product conjecture, you think it shows a good picture of what's happening?
Well, let's look at the pictures. I think it might be showing something. So today I'm pretending to not believe the conjecture, and in other days I pretend to believe it. But I'm not convinced. The arguments for Shoi-Moshi and the sort of 4/3 bound,
They're suggesting
they're
something else. They're not
suggesting something else. Yeah.
Yes.
So let's look at these pictures. So here is random subsets of n for n up to 2048, k going up to 32. So this is all of them shown on one picture at the same time. Let's see, as I shrink in, right? So these are just the 32 element sets, and the 31 and 30 and 29 and 28 and 27. And we can see, let me go to the small side. So as I gradually increase k, these sets are really definitely not going east, but they do kind of go north, and well, they decidedly come to the west. Right? By the end here, I'm getting lots of stuff down here. Oh, I mentioned, so this is Shoi-Moshi's 4/3. In these terms, it means that these normalized sum products, there's no limit point on the inside of this triangle. And then his other result from incidence geometry gives another triangle, which comes all the way down, that has the same property, no limit points on the inside of it. So this Shoi-Moshi void, that I'm calling it, really does look empty through all of these. Right? It's not just asymptotically that it's empty, it looks like it's just empty. And the upper void is not like that, though. This is a result from incidence geometry kind of thing.
What we're seeing here is that there are things that are a lot closer to arithmetic progressions than you would think possible, right? Which are still, I mean, it's you know, it's 1 plus epsilon rather than 2 minus epsilon, right? They're much closer to
Yeah.
arithmetic progressions than we were led to expect. They are very far from geometric progressions. Their multiplicative set is almost independent, but even that, I'm
Yes.
not sure that it's independent as you'd expect. There's a sort of thick zone over there where it's much smaller than 2.
Yeah, it doesn't look like it's getting pulled up to 2, even though there are theorems in that direction. Yeah, what you just said is correct. Right, so here for you know the 32 element sets, right? All of the product sets have an exponent above 1.6, but we're seeing all the full range of sum sets, from linear all the way up to Sidon sets, quadratic. Okay, so that's one way to think about what a random set is, right? You just fix some big N and you take k pseudo-random numbers from 1 to n and you work with it. Another way to do things is to look at sets of divisors, and this is in a different part of the landscape here. So these are sets of divisors and subsets of them, except for like 6 of them, as I said, but lots of random ones aside from that. And again, let's maybe start out at the beginning. So we see, you know, k equals 6. We're not getting the full picture here, but for multiplicative Sidon sets, and these are trying to drift. Well, they drift eastward, but then they stop drifting entirely. Right? They just stay there. So here's our full picture, and maybe I can zoom in here a little bit. Yeah. So I don't know if you have enough resolution, but you can see here that there are occasional points that are just barely inside the Shoi-Moshe void. Come back to that in just a second. Okay, so finally, let me stop flirting with you and show you the whole data set together, everything that I know. So these are 7. These are the 8 element sets. Here's that weird thing that's out on its own. Again, this Shoi-Moshe void, which, you know, his proof is asymptotically. Oh, let me tie this into something that Mel said before we began, right? So this upper void here says, so there's no limit point inside this upper void. So if you took a sequence of generalized arithmetic progressions with a fixed dimension, we know that the sum set is bounded by a constant times k. So in our normalization, that's going to be driven to be a 1. And by this void, that pushes the y coordinate up to being a 2. The product set has to go up to being basically quadratic. So Shoi-Moshe's this upper void implies that for a sequence of generalized arithmetic progressions with fixed dimension, the product set has to become basically quadratic. And at the other end, we get the same thing going for generalized geometric progressions. They have a bounded product set size, and so that's going to be driven down to a height of 1, and Shoi-Moshe's void then drives it east to being basically quadratic. So those were the extremes that pull things, but the extremes don't really say maybe what's going on in the middle. Okay, so let's keep going. This is 8 elements. 9 elements, 10 elements, 11, 12, 13. Now we're getting like little gaps on the inside. I really don't believe that that's the truth. 14, 15, we're getting, well, let me keep going forward slowly. 16, 17, 18, and you have up here for 18 element sets, we could call it a lake of ignorance. I don't believe that there aren't 18 element sets whose sum set and product set go there, but I don't know how to generate 18 element sets that end up there.
They have to be rare in some sense, or you'd be seeing them. I'm
Yeah,
not sure
rare
what
in some sense, right?
Right.
Oop. So let's keep going. 19, 20. My ignorance, turning from a lake into a river. It turns out there's a lot I don't know. This big shelf here was from looking at all subsets of the numbers from 1 to 36. Pulls things, and we keep going. And as K gets bigger, I get more and more red, the coloring, so that when I put it all together, you can see something. So let me see if I can make this a little bit bigger. It's moving slow because I'm using up so much memory. Okay, so you really can't see on this scale, but there are a dozen or so points that are just into the Shoi-Moshi void. As you look at these red points, right, so the redder things are, that's the bigger the sets are. And these red points, not only are they not going north and east, they're still coming south and west. So I'm getting closer, more points along just outside the Shoi-Moshi void when I look at 32 element sets than when I'm looking at 30 element sets, than when I'm looking at 25 element sets. And again, this is all limited by my imagination on how I can generate sets, but there's this huge void, this huge river of ignorance, I call it, coming through. And now I may have gone too far. It looks like maybe my Mac has hung. There we go. Something happened. So here are some of the sets that are inside the Shoi-Moshi void. So these are sort of, these are sets of positive integers where the sum set and the product set are both surprisingly small for given how big the set is. These I should be able to make bigger without breaking heads. So the last column, I guess, is self-explanatory. This n is the least common multiple of them. A thing I would like to point out about all of these sets.
Powers of 2 times powers of 3, right? I mean, these are special numbers. Yeah. Very structured.
Yes, but not just, right? So these are the property that pulls out to me of these is that they are divisor closed. If it contains X, it contains all the divisors of X. This is also, like, if you look at this last one of size 19, these are the first 19 divisors of 1728. That's another way to think about these sets, perhaps. You're looking at a set of divisors, the first so many of them, and they get you to be somehow extreme. Okay, so some leftover thoughts here. I would really like to have an idea on how to generate sets in the river of ignorance. I guess, so the point I want to make is that as all the ways that I know how to generate sets, when I look at it all together, I'm getting points that are, not only are they not going north and east, the extreme south and west end seems to be coming more south and more west.
Well, converging on the boundary of the void, right?
Yeah,
Maybe.
yeah. So, but it's worth noting that this void of Shoi-Moshi is not, it's not best possible. I listed in the history section, there have been ever so slight improvements of that on the order of like 1 over 10,000 and then 1 over 5,000 and then.
Right, but as you said, in terms of the pictures, it's more or less that. It's
Yes.
The difference is negligible. Somewhere near there seems to be a boundary that's for real.
In fact, in everything I've generated, it supports this conjecture that I've highlighted, that A plus A times AA squared is at least this expression. So in contrast, Shwemoshi gives here K squared over log K, or sorry, K to the fourth over log K. And this is just K to the fourth times 2, basically. So it's, and 10 trillion sets. I haven't found a counterexample. There was this question at the very beginning that, yeah, you do need to, there are differences where you're taking your sets, that reals aren't different from algebraic numbers, but there are differences between taking positive integers and positive reals. If you allow 0, then other things can happen. I don't really understand. I haven't looked at all at what the pictures would be like for those kinds of sets. Here's a nice looking conjecture. This appearance of the golden ratio is whimsical. I don't think it's really that. Right? For each k, you can compute what the best exponent is allowed by this data set that has some 700,000 nice sets in it. And as k increases, this exponent decreases. This is another thing that's not consistent with the sum product conjecture. And it decreases, like it's plausible that it's decreasing to the golden ratio. It's I think the lowest, the decrease is steadily down to like 1.63 or so. And there we are. So this golden ratio, I don't mean anything too snarky about it. It's just draws attention like that. As I said, the extremal sets that I've looked at are these divisor closed sets. These are the ones that seem to be huddling along the Shwemoshi void. And it really, like, what's the right notion of a random set as far as this problem is concerned? All right, so I'm out of time, but I've got one more thing. I've got an encore, if you will, which I will do even though there was no
encore.
Thank you. Since you insist. This is looking at the first 205 3-smooth numbers, and they are plotted here in blue. And you see like some of these sets come through. So these are the first k 3-smooth numbers for k up to 205. And the first k 5-smooth numbers for k up through 860. And so on. So you see the 3-smooth numbers have their pattern, and the 5-smooth numbers are a little bit bigger, and the 7-smooth a little bit bigger, and the 11-smooth and the 13-smooth and the 15 and 17-smooth and 19-smooth is right on top.
What exactly are we being shown here? We're being shown the sum and product numbers for their sets of divisors. What?
This is the normalized sum product pairs.
Yes,
for the 3-smooth numbers.
What do you mean for the 3-smooth number? You mean, what did you do? What did you take?
So the 3-smooth numbers are the numbers whose prime factors are just 2 and 3.
Yes, I understand that, but what did you do with them?
So I looked at the first 5 of them, and the first 6 of them, and the first 7 of them, and the first 8 of them, and the first so on, up to the first 205 of them.
And you looked at those sets as sets, and you took the sums and the products?
Yes.
Okay, so obviously the products are going to be highly structured because we're sort of talking about a product of 2 geometric progressions. So
well, the product of if all the prime factors are 2, 3, and 5, then when you multiply them, that's still going to be true.
Just for 3 smooth, it's sort of 2-dimensional. You have 2 to the A, 3 to the B.
Yes.
So you're obviously going to have structure on the multiplicative side, but the fact that you get structure on the additive side is a little surprising.
Yeah, so the structure on the additive side comes about because you start out getting a whole bunch of them. And so you end up with this sort of arithmetic progression at the beginning that fades into being a geometric progression later on for bigger values.
Okay.
So as K increases, these dots are moving as it happens. This isn't shown in the picture, but as it happens, they're moving to the southeast corner, right? That's how these lines are happening, right? So for small K, we're up here in the upper void, and as K increases, then the chaos comes out, and you get a nice pattern, a nice streak coming down to the south and east, right? So when K is small, it's basically an arithmetic progression because all of the small numbers are 11 smooth, right? You have to go quite a ways before you start missing numbers. You miss 13, but that's just one thing, right? So you get this huge arithmetic progression at the beginning, and then as K starts to increase, it starts becoming, you get away from that beginning, and it's just this geometric effect, this stability of smoothness effect that takes over and pulls in the geometry. Was that at all clear?
Seems clear, yeah.
Okay.
So you're thinking you could sort of fine tune it, combine the two things to get arbitrarily large sets, which are somewhere in between?
Yeah, something like that. Yeah, so that's better than just taking the 17 smooth numbers, for example, is if you take the 17 smooth numbers and the first couple of ones that involve 19 and maybe the first one that involves 23. So it's not quite, I mean, smoothness isn't quite the right concept here, I think. You need some like sliding scale of smoothness for the sets.
Abound on the prime divisors in terms of the size of the number.
Yes, perhaps. But one thing you see on the picture is that if you fix the smoothness, then you get pushed to the east edge. And if you fix the size of the sum set looking through, then you get marched steadily up to the northern edge. So this picture actually looks like it is reinforcing the sum product conjecture.
The fact that it moves so smoothly in between the two suggests that you can go, get arbitrarily large numbers, which are somewhere in between. The very fact that you're getting so many dots in between the two extremes, and there's no gap showing up there, suggests that that no, you could fine tune things so that you have arbitrarily large sets, which are some midway between arithmetic and geometric.
Yeah, maybe. It definitely also suggests that that these two voids that Shoimoshi proved are like somehow they're more intrinsic, right? It's not just a limit of what he was looking at. This sort of corner where they meet is where all the chaos of smoothness is still happening for these different things, right? Different levels of smoothness. These are, by the way, the reason I chose these numbers is these are the smooth numbers up to 20 million. And so up to 20 million, there's 16,625, 17 smooth numbers. So the cutoff is uniform for all these different smoothness levels.
Let's see, Kevin, is that it? I just want to be
yeah.
able to thank you.
Yeah.
So, and these are really fantastically interesting pictures. So do you have like a spare computer which is running 24 hours a day to generate all this stuff?
I do, and it's right next to me, and it's running stuff right now.
So are you the first person to do all of this sort of intensive experimental work on some product? I mean, have you seen graphs and pictures like this before?
No, I haven't seen any graphs or pictures in any of the articles before. This work of Rice and a bunch of undergraduate students, they were looking at sets up to, I think, 10 element sets and looking for the first point along the diagonal. So that's, they clearly they did some experiments to inform what they're doing, but they don't really report much on the experiments in their paper.
So Kevin, when you're generating these random sets of integers, I mean, I'm curious because most computer random number generators work with like linear congruential methods. And I'm wondering if there's any notion that these might interfere somehow with the kinds of results you're getting, the fact that there is this sort of linear structure to how the pseudo-random numbers are generated.
Or
are you using something else to generate the numbers?
Well, I'm using Mathematica, which has a pretty thought out random number generator. But it is pseudo random. It's not actually random, and it's conceivable that would give some difficulty here. Although so I don't know the details of how they're doing it, so I can't really address that.
I mean, I'm sort of out of touch on this, but some number of decades ago, I was doing some work in biostatistics that involved we were generating lots of samples, and we ended up I had a student write his own generator because the generators we were using were not appropriate to what we're doing. And there was, and I assume still is, a pretty vast literature on generating sets of numbers in the statistics community. But because the classic methods all involve something akin to sort of piecewise arithmetic, well, not really arithmetic progressions, but akin to them, it feels like maybe there could be some interference, and that could be artificially generating some of these unexpected holes.
Mm-hmm. Yeah, so I guess the easiest way to test that would be to code it up in some other language, some other random number generator, and see if it's if I'm getting the same sort of phenomena, which I haven't done, but I'll take that under advisement.
Other questions for Kevin?
Yeah, I guess I have a question. Have you considered kind of creating sets from different methods and then just taking a union? Would it possibly have a chance to fill in some of those gaps?
Yes, so I've tried this. The problem is if you change a set too much, then it instantly leaps up to near 2 on one side or the other. And you just I just end up hopping right over my river of ignorance. So
I see.
Take things below it and try and perturb it a little bit. Sometimes it moves just a little bit and then it'll hop over.
So I see. There are no methods to take several different sets and combine them in a nice way, unless the sets are also kind of special position. I see.
Yeah. So I have done, a chunk of my everything everywhere all at once picture was where I was taking arithmetic progressions unioned with geometric progressions and just scattershot, try them all kind of thing. And it really disappointingly didn't add very much past what the sets of divisors had already given.
Mm-hmm. Thank you.
Thank
Other
you.
questions? If not,
Uh,
let's
so-
thank Kevin again.
Oh, I have a horrible question. I have a horrible question.
Go ahead, Dennis. What's horrible?
Yeah, so you were talking about the sum product conjecture. Totally naive question I haven't thought about. What if you change the sum set to the different set, or or what if you change the product set to a ratio set?
So that is looked at. A lot of results in the area are comparing A plus C and A times B. Right, so you're even on an additional level of generality going on for that, right? And that captures different sets and quotient sets. As far as what happens experimentally, no idea, right? So on some level, you start conducting this experiment, you've just got to make some choices, like, are you going to allow 0? Are you going to take integers or positive integers? Or and there's life is too short to look at all the variations, and so I just kind of guessed what the interesting one would be, and good chance I was wrong, but
I mean, there
Well,
are
this is very
results that
interesting.
people look at quotient sets, for example, but I just don't remember what they are.
and there has been some work in the sum product conjecture just in arbitrary rings. I think Terry Tao has a paper seeing what he could do, pushing the methods into arbitrary rings.